The pressure is on now.
No, you don't have to
Well,
feel pressure because, it's a mess for me in the morning to try to explain all the knitting techniques in English. So don't worry.
I'm not worried. It's more of the
yeah, and
same.
it's being streamed on my YouTube channel, which is not very
All good.
well known. No, I have 0 followers, so nobody is really watching these videos except for our students. So that's good.
Okay, that's nice. No, it's all good. Even if they are, there's nothing crazy about it. I suppose everybody's a bit tired. I know you said 20 minutes. I prepared something. It might take me a little bit more than 20 minutes, if that's okay.
That's okay. No rush. You don't have to rush through it. Just take your time.
No, and I mean, it's more of the same things that maybe everybody has already seen a few times, but I thought it's nice anyways. So
I don't know. I mean, some of our students are actually from fashion design, so they may have not seen some of this stuff. So they've come from very different backgrounds as well.
Okay.
So it might be quite new to some of them.
All right. Great.
Can we get started? Do you want to share your screen? I guess for the students that are here, if you haven't figured this out, this is Mariana Popescu. And so she's one of the leading researchers with knitting these days in architecture. And she finished her PhD with a really wonderful project, the Knit Candela, which was a collaboration between her and Philip Block Research Group and Zaha Hadid Architects, Zaha Code. So we're really happy to have her talk about all of her research and process. And I think you heard us mention her earlier today when we were talking about knitting structure, and one of the papers that she had written on this was really influential to Giga's work in developing knitting structure as well. So welcome, Mariana.
Thank you for having me. It's really nice to see you guys. I'm going to share my screen. And I'll be talking a lot about knitting, let's say, but through the framework, through the eye of construction. So really trying to use knitting in the context of saying we're going to challenge the construction, logistics, waste, and economy of concrete formwork. So what I work on a lot is concrete formwork. So the knitting that I'm showing you is in this context mostly. And at the end, maybe you'll get a glimpse of something that has nothing to do with formwork, but is still a lot of knitting. So as I mentioned before, what I would be talking about today is mostly focused on the challenges associated with building complex concrete structures, and why I'm looking into that is because usually in architecture, if we do want to build efficient structures, that means that so that use less material, and that we need to do that from a sustainability point of view. So structurally efficient and materially effective structures usually have doubly curved geometries or intricate geometries with rib stiffeners. Those are mostly the structures that you see on the right side of your screen. So the Felix Candela type structures, doubly curved thin shells that can span really long spaces, or the Palazzo dello Sport from Pierluigi Nervi, where you can see it is a dome structure, but it has all of these articulations and rib stiffeners that make it a more intricate geometry to build. Now, regardless whether it is actually a structurally or materially efficient design, you can also just have doubly curved designs in general, and those are usually materialized with concrete, because concrete can be molded into any shape, literally any shape, since it's kind of liquid stone to begin with. But the catch is that we can do that if we have a mold. And if we have a mold is where the trouble starts. So the molds that we usually see for these types of structures may have come a long way from 100 years ago, or the kind of things that, well, 150 years, 50, 60 years ago, 70, well, we're getting into that range. But in the last century, which you see on the right, that are quite intensive on the formwork side, we've come some way in terms of being a little bit more precise with our formwork and being able to really manufacture that in a very fast and precise way. But at the end of the day, if you look at it, it hasn't really, the basic principles of it haven't really changed much. You still need a lot of scaffolding to hold up these clunky, heavy molds to be able to make your structure. And in the case of custom doubly curved structures, that means that you only use it once. So that turns also into a pile of waste, and that is a little bit of a problem. Now, it is not really a surprise that formwork is a little bit of a topic in the world of construction and architecture because of these things. So there's a lot of research being done, both in academia and in practice, on how we can build better, how can we have better formwork solutions. And these types of solutions usually focus on, for example, how can we build how can we make our formwork faster or lighter? How could we maybe reuse that formwork so that it's reconfigurable, so we don't need to waste it or throw it away? 3D printing makes it possible to really build almost any geometry you want. So we can really make all of that complexity through this 3D printing type process. And others also look into how that formwork could be actually left in place, stay in place. So something that is more becoming part of the structure and having also a structural influence. So it could be reinforcement, for example. So it's not wasted. That's the more traditional approach. A different type of approach would be to use fabric or a membrane to do this. So those are flexible formworks. Flexible formworks, as I've said before, and now you see in all of these images, are ones where you use a membrane and you tension that membrane somehow into shape. And that could be by draping or hanging over an existing frame. It could be done with inflatables, so you inflate it into shape. It could be supported by cable nets or splines or bending active splines to get to the shape that we want. Or it can be really tensioned into shape with frames, with rigid frames, so with little rigid frames on either side to really give it that shape. And then the flexible formwork is being used as formwork for concrete. Now, in moving away from the traditional formwork systems, the one that I've showed initially, and going towards a flexible formwork system, there are some advantages. In terms of lightness, so a textile, whatever type of textile, is a lot lighter than wood or foam, which is usually what is being used for these types of molds. It needs a lot less support from the bottom, and it doesn't produce as much waste. Of course, there's a catch here, and take this kind of sketch a little bit lightly, right? This sketch that you see here. Of course, there's a catch, because you can, with the traditional type of formwork, it's let's say the brute force approach. As long as you are able to manufacture that mold, you can also build that structure. So as long as you do that, you can hold it up and make the structure. But with a flexible formwork system, you somehow have to also, you cannot build just whatever type of geometry. You have to take into account the form finding, which is what you've probably also started to learn during these first few days, into how to get to that geometry. Now, this kind of limitation, I like to call a blessing in disguise, in the sense that usually that means that we also need to be smarter about the types of structures we design. So if we want to take advantage of having a less wasteful and lighter formwork, then we also have to design better structures that are then thinner and more form found, which is also why you see this distinction in this type of sketch. I specifically look into knitting for these types of membranes. The reason for that is because they are very versatile. I usually like to give the example of shoes, because that's the most known example for everyone around. And it's just why that is interesting is because you can have, with a knit, you can have full 3D shaping. You don't need as many stitches, so you could do a 3D shape without stitching different parts together like you would tailor clothes. You could do branching structures. You can have channels, pockets, openings. You could also make spacer fabrics, and perhaps one of the ones that I find very interesting about this, and it's if you look in the bottom right corner, is to be able to have tailored material properties. So it's kind of what makes you think of a lace. What you can do with knits is you can really add the material where it's needed and have it more porous where it's not needed, and so on. Now, it's not that other types of textile formations cannot do these types of individual things. So you can make spacer fabrics also with other types of fabric formations. You can have also tailor material placement with other fabrics. What is very interesting, though, with knitting is that you can really bring all of them together with the 3D shaping in one single process. So the way we approach things is we start with the design in the formwork. That design is informed, as I kind of explained earlier, so a form-bound design. And that design then, for that design, you produce a fitted textile, which is done through knitting. That textile is then tensioned into a frame, for example, or however it is, however we choose to tension the textile through different examples. And then it's coated with a very thin layer of cement or resin. And that is because for all of its advantages, knitting also has the disadvantage of being incredibly flexible compared to other textiles. So it means that it has this flexibility that would mean that it deforms a lot if you try to cast concrete directly into it. So we build up that initial strength with a tensioning and a coating. Now that coated textile becomes the formwork for concrete, and it can be used then for casting normally. There are two crucial steps in this. The first is having a design and coming from the design to the knitted textile for that design. There are still two steps to that, roughly speaking. One is to discretize the design, because even though we can make directly 3D geometries without a lot of stitching, architecture usually is of a very large size. Your machine is kind of a way smaller size, so you would still need to discretize that design into pieces that are manufacturable on that width. And then for each one of those parts, depending on the size, we need to generate this knitting pattern or the instructions for the knitting machine to actually produce the textile for that part. The second challenge is how to go from having the textile to the formwork itself. So those are the two parts that I would be talking about today then. Now, on the second side, there are two options. Textiles are really easy and light, so they're compact, they're easy to transport. They could be shipped very compactly to the site where it's then tensioned and coated, and that makes the formwork. Or the other avenue would be to tension and coat the individual parts in a sort of prefabricated environment. Those thin coated textiles are also very light and can be easily transported in a component sense and assembled on site to form the formwork. Either way, this becomes the formwork for concrete to be cast in to create the final structure. So, why can knitting do all of these kind of things? You've probably gotten a lot of this information now also from Ige and Virginia, but I'll go through it anyway. So the reason, and I'm talking only about weft knitting in this case, which is also what you guys are using in the workshop. The reason for this is because knitting has a weft and a work direction and is defined by a unit, the unit being the loop. Now, if we look at that loop, we can see that it's characterized by a width and a height, so a course spacing in between all of the courses. And what you can already see a little bit being hinted at is that we can abstract a 2D textile, a knitted textile, as a 2D matrix of rows and columns. Now, for a plain textile, that would look something like this. If we wanted to start creating geometry, so if, let's say, we wanted our textile to have a shaping in plane, there are operations for that. Those are so-called increases, so adding a loop, or decreases, removing a loop from each one of those courses. And of course, then there's that still leaves a 2D-ish textile, even though it's contoured. And then the question would be, what happens if we want to make a 3D pattern? And if you want to make a 3D pattern, so say we have a geometry with a bump, as we see here, we see that the matrix that describes it at the basis is kind of the same, but we notice that the back length of our geometry and the front length are 2 different lengths. So somewhere in between these two, we need to find a place to add extra material. And this addition of extra material can also be done in a number of loops on that course, and those are usually called short rows or shaping rows or courses. This is kind of the strength of being able to create 3D geometry, because in normal textile patterning, otherwise what you would do is cut out this little V and place that little piece of extra material, stitch it together and get your bump. But in this case, you can do it just by adding locally those loops. So as you've also seen in your visit, those kind of textiles get produced by these types of machines. They are all from different manufacturers, but the principle is exactly the same. So you have a number of needles arranged on the needle bed, which catch a thread to pull these consecutive loops one through the other. Now, what is interesting about it is that you can, because there are needles facing each other, you can create an individual textile. So you could have one yarn working on the front bed, creating a textile. You could also go back and forth between the two. You could separate and create, as it were, 2 parallel textiles, one next to each other with 2 different yarns. So there are a lot of different operations that you can achieve with these types of industrial machines that also make it possible to create all of these types of features. So as before, the instructions for the machine can be abstracted as a pixel grid, where every row is a pass of the machine and every pixel is an individual needle, where every color is an individual operation that needle performs on that step. Now, usually these patterns are intricate, and they are created in a sort of manual process by skilled technicians that know exactly where to place these types of features. So for example, here where you see can you see my mouse actually? Yeah, okay. So here where you see no pixels, there is no working of the needle. So that's where no extra loops are being created. So this is what you would call then a short row or a shaping row. So that becomes one of the processes that is very difficult to do on an architectural scale, because if we do have to think of knitting patterns for primitives that we know, so geometries like a sphere or an ankle or a tube, we might imagine where these types of features need to be placed in order to get that 3D geometry. But when we get to the architectural scale, our geometries are not necessarily based on primitives. They are not only not based on primitives necessarily, but they are also a lot larger than the usual sweaters or pieces of textiles or shoes or pieces of textiles that we are used to. So creating that intricate pattern of knowing exactly where to place every single feature becomes really complicated. So to be able to really use them for construction, this bottleneck of creating a knitting pattern in an automated way needs to be overcome. So the question is, how do we go from a given 3D design to a knitting pattern that can be fed to a machine to then get the knitted object that we want? So for that, I wanted to show you why is it not going on? There we go. So one of the questions that I tried to solve in this way computationally is, how do we go from this 3D geometry to the corresponding pixel grid that can be fed to the machine to get our geometry? So to do this, I'll give you the example on the node. The first step would be to patch the geometry or to split it into a number of pieces. That depends on the size, so whether it can be produced in one piece or not, or just simply for being able to generate those patterns. So for example, I could have chosen to generate the patterns for this node that is done in one piece in several different pieces, even though they become one code for the machine. Then for each one of those patches, we generate the courses, or the so-called passes of the machine. And within those courses, then generate the each loop, so each individual loop that belongs there. And this is all done on the 3D geometry. It's done as a topology, so it's kind of similar to a remeshing, where you at the end you get a mesh that is a combination of quad faces and triangles, and that topology can then be translated into a 2D pixel pattern, because we know the relationship between each one of those faces. So I'll give you very quickly the example on this, say, this one patch of the node. We select one patch. We have to, because knitting is defined by this loop geometry, we have to select our loop. So what is the height and the width of the loop that results, and the knitting direction, because unless they are square, which they almost never are, we need to know in which direction we will be knitting this. So knowing the knitting direction and the sizes of the loops, we can start generating those patterns. So knowing the start and the end, we can create all of the individual passes. But what you notice already is that not all of those, it's not a 2D geometry. So not all of those passes go all the way through, so that we can create those short rows or those inserts of extra material here and there that can that allow us to make 3D shaping. Now, once those all of those courses were generated, within those, we sample those with the width of the loop, and then we generate all of the different loops that are within each one of the courses. So what you notice here, though, there are the triangles, and the triangles represent those special operations that allow us to do the shaping. So in this case, the blue ones represent the start or the end of a short row or shaping row, and conversely, in the other direction, the triangles can represent either a increase or a decrease into our shaping. So now that we can go from a given 3D geometry to a pattern and knit the textile, the next question is, how do we get to the formwork, right? So we've gotten the textile, how do we get to the formwork? This was one of the first tests to see that the knitting pattern works, and the first coating. It was done on this lovely Brother knitting machine by hand. So it is quite laborious, but it's a very good learning process. And what resulted is a very lightweight node that can be then that is stiff and can be used as formwork. Now, I wanted to show you two projects. One is the first one that was meant to test this type of concept of how to build up strength in layers so that it can be used as formwork. It's a small knitted bridge, which was built by tensioning a textile with splines and rods into a corrugated shell, and that is then coated with a little cement paste and a little bit of mortar to build up the strength, and then concrete can be applied, can be cast normally. What is interesting about this particular textile then, compared to the node that was just a simple test, is that it has already the channels integrated into the textile to be able to add the glass fiber rods, for example, that were used to push up the geometry, the aramid cables that were used to pull down the geometry to create the corrugation. What you can also see are they were little holes in the textile that have been plugged, so that we have holders to know how thick our layer needs to be, so how thick our concrete layer needs to be. And even though it's maybe a little bit obvious, especially for those that are studying fashion, this is a ribbed pattern, but that also is deliberate, as it helps with the flow of the coating, so it doesn't actually go all the way through in a very easy way. The patterns for this bridge looked something like this. So they were it was made in 3 pieces, and that had something to do with the width of the machine. And you can see all of the pink rows are the shaping inserts, so it's not a 2D piece of material. And then all of the blues mark the channels where all of these kind of things go through. I'll skip through this very fast because this is just how the process of knitting all of these parts. You can see already the holes in there in the specific places in the channels, and putting it together. What is maybe less obvious in this picture, but if you look closely, is that it is not just a flat piece of material, but there is extra material here. It just looks flat and crumpled in this particular picture. And you can see that the channels are laid out exactly where you need to have them. So they are tailored into shape. So what we did was we tensioned that into shape. It looked something like this, a corrugated geometry. We then took that into a climate chamber and applied a relatively messy coating, but it made a very thin cement paste so that it didn't deform the textile. That turned into a stiff enough, rigid enough just to support the next layer, which was a layer of shotcrete. And that made it about 3 millimeters of formwork. And then this formwork is used to just cast concrete normally, the most traditional way possible. This is the bridge that comes out of that. And what is very interesting about this from a construction point of view is that there were no supports on the bottom right. So all of this was just supported on the two sides, which shows that there is enough, let's say, advantage in not having all of the supports from the bottom and being able to deploy this over a given span without needing to stop, for example, water flow or traffic if it would be a real bridge structure. This is my colleague Lex. He is usually responsible for coming up with a very special formulation of this thin cement paste coating, so that works very nice and strong. So we were very happy and also load test this by jumping onto the bridge, but I always like to show Lex in it as well. What this bridge also showed us was a little bit of a glimpse into how we could use the textiles aesthetically as well, because it is coated only on one side in this case, and that gives you a glimpse of the structure on the other side. So we took this input and wanted to show it beautifully in the next project. So the next project that I wanted to show you was the Knit Candela. It was built in Mexico City, as I mentioned before, in collaboration with Zaha Hadid Architects Code Group. It was for their first exhibition in Latin America. It is inspired by it's called Knit Candela because it is inspired by the famous Spanish Mexican shell builder Candela. It's a sort of homage to his way of building thin and optimal shells. What is interesting about it is that it was built using a cable net as a false work. So the textile was tensioned into shape using a cable net and the knit, and the cable net and knit together weighed only about 55 kilos and carried the weight of the five tons of concrete. What is also specifically interesting about this shell is that it's a ribbed shell. So it's a thin shell with stiffeners in two directions. Now in this section, you only see the one direction, but it has stiffening ribs. So the challenge here is not only the global 3D geometry, but also the local geometry of adding all of these pockets in the right place. So how this was constructed was by tensioning a textile into a frame. That textile had already cables in two directions. So you can see the cables here and loop cables going around that helped tension everything and were the main load-bearing part. The textile had the pockets or the channels for those cables and also pockets to add inflatables. And those balloons created then the cavities inside the concrete locally. It was coated just as before with a fast-setting cement paste. And once the fast-setting cement paste hardens, concrete can be cast onto it normally, and it creates the geometry of the shell. With the concrete having hardened, we can remove the frame and you have the shell there. The inflatables also serve no more role, but the textile stays in place. So what you see actually on the inside, so this blue line that you see on the inside is actually the textile that you see on the inside of the pavilion, and the concrete that is visible on the outside. So what is special about this textile is that it fulfilled two functions. One of them was an aesthetic function and the other one was a technical function. So it has two different sides. On the technical side, there were pockets with openings to be able to insert the balloons, channels with openings to be able to insert all of the cables and tie them together, and also different material densities to have to control on which side the pockets inflate the most. So if we have a look at the front side and the back side of the textile, we see that they are quite different. As you can see here, there is more material, there are openings and there are channels, and on the front side you see only kind of a hint as to what is going on behind, just as an intelligence of it. But what is interesting about that is, right, that there are two different materials and there are all of these features and they are produced just in one single process. And for that, we still had to segment the geometry into 4 different strips. We took advantage of the fact that knitting is an infinitely long process like a plotter, but it only has a particular width. So it was 4 strips of 16 meters to 26 meters. For each one of those strips, we generated the patterns. This is just 1 4-meter part of it, because otherwise it would be very difficult to even see what the patterns are on the screen. But that is an example of what a pattern would look like. And you can see all of these shaping rows and all of the placements. And you can see a hint of where the pockets are supposed to be and where the channels are going through for the cables and so on. So if we have a closer look at this, you can see where the patterns also come back into the textile. So let's say the pattern, and we see that side by side with the back side of the textile. You can see that this is what defines a channel. This is what defines a vertical channel in that case. This is what corresponds to an opening, and it was maybe a little bit. It's not usually easy to see. Maybe it's easy to see on the front side. Usually you can also see the short shaping rows somewhere around here, but it's a little bit difficult to see in this picture. So what those little pixels here of different colors and their combinations show are something like this. So they are developed a library where we have knitting that is done on the front and back. As you might remember, there are 2 colors. There's a blue and there's a black. So each one of them was done on one of the beds of the machine. So for example, a salmon colored pixel would mean knitting on the front and the back with 2 different yarns, or knitting back and knitting front, but reversed. So blue on the front and black on the back. A different pixel might mean knitting just on the front and not knitting on the back, or knitting on both and then transferring 1 loop from the front to the back, knitting and dropping a stitch. This is to be able to create a different density, for example, and knitting and adding and moving to the side. So these are just some examples of the types of operations that you might encounter in that type of pattern. So when you start thinking why this works is when you start thinking of having these kind of pixels side by side in one pass of the machine. This is what that might look like, right? So we have knitting front and back and front with the different colors, and you see that next to each other, and you start seeing where these types of things form. So you start seeing why this starts becoming a channel, because we switch where the thread goes to the front and where the thread goes to the back, and that locks it into place and creates an opening here, but not an opening there. What you can also start seeing is that you can have one density on the front and you can have a totally different density on the back, because we're not knitting all of the needles on the back, but we are knitting all of the needles on the front. So there it is, that's a channel. Those patterns were then given to the knitting machine that we have, and we produced these four pieces of textile, arguably the world's largest, I don't know. And then here's Lex again. We packed those into four little vacuum bags, put them in suitcases, took them to Mexico in our checked-in bags. They weighed only 25 kilos, but we don't fly business class, so then we had to have 2 bags. This is the textile that was then in Mexico assembled, so all of the 4 pieces stitched together on the floor, and then here you can see us probably putting the cables through all of the different channels. You can see them coming out here. We temporarily fixed them into place where they should be, and then took this and put it outside and tensioned it into the frame. This was also the first moment that we could breathe relieved, because it did stretch. I mean, it looked really small, right? But it did stretch to the right size. And it did work. What is also interesting, why I particularly like this photo, is because you can really see how light and minimal the formwork becomes on the inside. Meaning that yes, we do have this frame that's holding it all together, but if you try to imagine how you might get this geometry out of milled foam blocks and how that needs to be held in place, it starts becoming a totally different story. So this is a very nice picture for me, for that it was the moment that we could see that it did work, the second one, because it is actually very light. Here you can see Lex coating the textile on the outside, and you can see a glimpse of the pockets that are starting to form with the inflatables. These pockets, as I mentioned before, become the cavities inside of the concrete. So this is the formwork that then the concrete is applied to. And what is particularly interesting about this is that usually with digital fabrication, there's the paradigm that we can, that a machine doesn't care if it makes 500 times the same piece or the same rectangle, or 500 times a different one. So we have the economy of scale in that sense. But the problem that we do have then is that of logistics. So we do have 500 different pieces, and we have to make sure that they end up in the right place. In this case, that logistics has been taken care of by the textile, because the pockets are all the different sizes, but the balloons that we put inside are all the exact same type of balloon. So it's just the textile that takes care that it inflates to the right size and to the right side. So here's the concrete being applied to it. And that's just a glimpse of what it looked like in the end. What I do find maybe a little bit less intuitive in the video is that you cannot see behind this textile, but when we were there, you could push into it and it was actually soft because there were these cavities behind it. Depending on how the sun would shine, you could also even see that there's a pocket there. Sometimes also the skeleton of a balloon that was deflated inside. And that's the project itself. So just some takeaways. It took just the formwork and the cables cost for 50 square meters about 2,500 francs. So that is very, very little compared to what you would need to out of foam or timber. The textile only weighed 25 kilos, so it was very easy to transport. It took 36 hours to manufacture the textile, so it's 36 working hours of the machine, right? Versus 750 hours, what you would need to create a milled formwork otherwise. And the whole project from start to finish was 3.5 months. And if we take into account that from start to finish, meaning from the first design meeting to the structure standing there, was 3.5 months. So if we take into account that the 750 hours are more or less 3 months, it would have really been impossible to do this with traditional formwork techniques. But what is mostly interesting about this type of approach is that we always there are factories with hundreds of these machines, the instructions, and it's kind of what you guys are doing also now in the workshop. So if we have a way to create last, what I wanted to show you is a more recent project. They're tailoring. It's a small project that is on show at the European Cultural Center in Venice during the Venice Biennale, and it's done in collaboration with Anna Goidia and David Andreen from. I'm not showing you they built a wall. On the back, and that wall has a particular has a textile fronting on the front. What is interesting about this is that it's exploring the possibilities of using of really tailoring material properties. So what you see here is that this has a lot of it has different textures, so different densities. It might be more difficult to see in one glimpse, but there's one density here, there's a different type of density or structure there's yet another different type of density, that all have different properties in the knit. on the wall. It also has specific inlays for the attachments so that you can attach it, and it has openings and channels for attaching it and for going very precisely around fittings, since it's supposed to be a wall. With that, I would finish my presentation. I hope I didn't go too long overboard. I don't know what time it is. I'm very happy to answer any questions you might have. Thanks a lot.
That was great. Thank you. I think from our standpoints, like, very amazing work, and you've won awards for this stuff. It's been beautiful, but I do want to give the platform to the students, I guess, to ask any questions first before I'm sure Yiga and I would jump in with 30 questions. So do any of the students have any?
Yeah.
Maybe they're also too shy.
Don't be shy. I don't bite, and if I do, I'm too far away to bite. I promise. I'm very happy to answer anything.
Hi, Maria.
Hi.
I have one quick question. So I don't have an architectural background, so I'm just wondering, the balloons that you inflate there, are they to allow the concrete to dry or something? Because first I thought it was something structural, but then you also have everything else tensing the fabric. So I was just wondering, what's up with the balloon?
The balloons are to make the cavities. So it's on the inside.
What do you need the cavities for, I guess is the question.
What I need the cavities for. The cavities are material saving. So if you would make the same, type of structure, but then filled, you're using a lot of concrete, and you don't. That's kind of dead weight because it's not necessary. So it's material saving.
Okay. All right. Yeah. Thank you.
I think, Mo, if you've probably seen ceilings that have these kind of like coffered shapes in them. They've got little holes and structure. Like, I'm thinking really famously, like the Yale Art Gallery by Louis Kahn is a really beautiful one, but they are structurally, because it adds thickness where it needs like a lot of concrete and then takes away the concrete where it doesn't need it. This way it provides those kind of pockets to make it lighter. And I'm not a structural engineer, so I'm doing my best describing it.
No, it's perfect.
Yeah, from not having an architecture background, you maybe have never noticed these things. As architects, we're trained to see these things all the time. But you've probably, like, if you look up, you'll see a lot of concrete buildings have these kind of cavities in them, and it is for that same reason.
Okay, thank you.
No worries.
Great question, though. Any other questions?
Maybe their minds are blown off because most of the students don't have much idea about what knitting can do, and fabrics are also not a very familiar architecture material. Yeah.
Which is too bad, because historically it is actually quite a vernacular, I would say, vernacular material then, or maybe that's the wrong word for it, but it is quite an architectural material, but that we've forgotten to use.
Yeah, it has a very long history, but
yeah,
always related with Asian things.
You're right.
I have a question.
Yes.
Yeah.
Can you hear me?
Yes.
I'm curious, what's the limits and advantages compared to the 3D printing the knitting has? And I think they do not have the same degree of freedom. So I think maybe some advantages that knitting have and they can do and 3D printing cannot.
It's a very good question. It's tough to answer it, because they're being intrinsically used in two different ways. So knitting is a form of 3D printing. Let's say it's kind of like this, because you're building it layer by layer, row by row, pass by pass. Now with 3D printing, you can make more or less any geometry. I'd say with knitting, you can also make a lot of geometries. Maybe there's a limitation in which type of geometry you can make, which way, but it's most of how you would like to use it. So if you want to use 3D printing directly, it has its own layers, its own weak points. If you want to use it as formwork, even though there's a lot of work being done on that, it's also heavier. But they're just used in different ways. And there is no better or worse, I would say. I think they're always complementary. They're always complementary techniques. So they have their own place. Knitting also has its own limitations. You might be able to tailor its material properties easier, but it's not as fast in some. No, actually, compared to 3D printing, it's very fast. Never mind. Scratch that. 3D printing is rather slow to create. So if you wanted to 3D print the knit candela, it would have taken a lot longer than 36 hours to do that. So I'm not sure I'm answering your question, but
yeah, I understand. Thank you.
I have a question. I just wondering how to clean the knitting structure, since we know clothes will get dirty, and sometimes if somebody get coffee or eat something in the pavilion and the structure become dirty, and how to keep it.
That is a very good question, and it's also a question that I think of all the time. It's like, yeah, everything is great until the answer is, how do you clean this thing? So there are two answers to that I have. One is, well, we did clean knit candela with a pressure hose, so you can, because it's tensioned. I don't think they are necessarily durable structures if you can't unmold them. Durable in the sense of aesthetics, so it's staying clean or free from cuts or vandalism or whatever else you might think of that happens in a building. So I would say generally, I don't think the solution is to have an exposed knit. You just cover it on the other side as well. You just coat it. Pretty much, you just coat it. Now, you can coat it with the resin and then you can still see the knit, but it's coated somehow. The other option would be to make it unmountable. And that's kind of a little bit what's happening in the last project that I didn't show very much about it, but in the last project where it's actually just where it's just a front. So if you can unmount it like you would unmount any other sort of textile in your home, you can just throw it in the laundry and mount it back on. But then it's more decoration than, but it could be made in a modular way so that it is unmountable. But I would say the way you do it is either you coat it and accept that it's not actually visible. And it doesn't have to be, right. The aesthetics of at the end of the day, kind of what I'm looking into is how do we build more efficiently? So that happens to be with a textile. I find them beautiful. So I think there's an avenue there for the aesthetics of it, but it doesn't have to be visible. So it can just be coated and part of the structure.
Okay, thank you. But I also wonder if somebody smoke and say, okay, what a beautiful, and breaks the structure, because I know it's what happened in the city.
Yes. No, so that I would count under vandalism, let's say. It won't affect it structurally because once it's built, it's built. Textile doesn't do anything anymore other than be pretty, let's say. But yeah, the durability in terms of it staying pretty for a long time is very questionable. So yes, somebody would make a hole in it and it would unravel and it would end up looking bad. So it's definitely not a solution for that.
Okay, thank you.
Good question though, because I think there are some limitations, right? But that's why there's still a lot of research going into this, because we can still make it better and find ways to overcome these things, like by making it removable so you can wash it, or you know,
or
what are the possibilities? Also, I'm wondering about what materials you knit. I have questions, but I'm already like asking my questions of like, you use two different yarns, right? So you had like a black backing yarn and a blue front yarn. Like, I don't know what types of yarn those are because you didn't mention it, but maybe some yarns are less flammable, or like wool is not very flammable, or some yarns are sturdier for certain reasons. So this could also be some of them. And maybe there are yarns that haven't even been invented yet, right? So there's a lot of possibilities there. But I guess my question would be directly to like, what types of yarn were you using for like was it just color choice, or are there like ways that the black yarn stuck to the concrete better, or anything like that?
Yes, so they're pretty simple yarns, but it's all PES, so it's polyester. The choice for polyester in this case was for a few reasons. So one, the knit in this case is not structural, so it didn't need to be a very technical material. But what it did need was to be UV resistant. So, I mean, it was in Mexico in the sun, so you want it to stay kind of nice and not have that problem. And then generally, when you do want to use these things with concrete, you want an alkali resistant fiber so that it doesn't get attacked by the concrete. Now, if it's just a formwork, it won't get attacked by the concrete in the 1 week that you need to cast it or something like this. And in the long run, it doesn't do anything anymore to the structure. But if it is a structural material integrated within it, you want it to be alkali resistant. So the polyester happens to be alkali resistant and UV resistant. So that worked. It's also pretty easy material to come by and gives a lot of color options. Now, the difference between the front and the back is that the front is just PES because it looks nice. And the back is a mix of PES and a acrylic fiber that has a little bit of, that's not as smooth. And that was just the texture of the yarn itself, because PES is a lot more smooth, and the other one was a little bit fuzzier or hairier because it was a twisted yarn. And that gives it a little bit, it made it easier to have a little bit of water for the hydration of the cement paste, and for it to stick a little bit better. It stuck better than to the PES. That's for the knit candela. The bridge was aramid fiber, Kevlar, and that was not necessarily because it needed the reinforcement that way, but it was a test of being able to do this also with technical fibers and something that is virtually further. So for structures, it's a bit easier if you have a yarn that is not very elastic. That was this. And then I've tried things with cotton as well, but basically, and more recently, because we're working on making the textile also reinforcement, there's a combination of having PES and aramid, carbon, or glass fiber. And I've tried some things with basalt fiber as well. The conclusion is that you can use, in the end, whatever you want, as long as it can go through the machine, and as long as it doesn't get too damaged in the process of pulling the threads. So, for example, carbon fiber is not very great with that because it's brittle and it doesn't like being pulled this way, which is what the needles do. But you can still knit it, but it loses a lot of its strength.
Yeah, very interesting. I'm also thinking about like natural materials, and like if you're casting on it, there's that opportunity that you use it as a formwork, and then with a natural material, it would eventually biodegrade or start to disappear. I don't know if there's even like better materials that like really literally like dissolve, like when they do those stitches when you have like dental surgery, they do stitches and those stitches dissolve. Like I wonder if there's possibilities with that too, which could be quite interesting. You know, it starts to rain and then the formwork's gone or something. Definitely.
There are, and we've also looked into it. The challenges with that are actually the second step. So you need to coat it somehow.
Yeah.
If you coat it somehow, then it's not going to dissolve unless your coating is dissolvable, and that's a different material, and maybe that exists as well. But I think that is definitely a good way to go. So it's a good way to look at things, at how this could be unmounted. And then there are also all types of commingled yarns, so that already have a coating on them that you can harden and so on. We've looked into that as well. It's really, the possibilities are endless somehow.
Thank you very much for the lecture today. I've read a lot of your work again and again, and still I can get new inspiration from your speech today. And so my question is like, what's your next move for this knitted fabric formwork? Because to me, this is really an exciting movement towards a sustainable construction of concrete. We see so many wood wasted for the one time of formwork, and if yours can be something widely adopted, it can save forests and a lot of things. But I'm wondering what's the gap currently from your what you have already achieved to the real world, and also do you have any plans to further improve that, or maybe do you have some difficulties that I like to hear that, so maybe yeah, to get realized, because you are already moving to the very end in front of us, so you know more challenges in front of us. So we would like to know what's exactly lying behind us to realize this very exciting thing formwork into the realistic world.
I think there are a lot of challenges. So it's a very good question also. So there are, let's say there are challenges on the design side that have nothing to do with the knitted formwork necessarily. But let's say there are challenges on how do we design better. Then, of course, there are challenges on how do we design something that can be done with a knitted textile, because you can do a lot of things with a knitted textile, but then the types of systems that you use this. So there's a challenge there. And I think that's an ongoing, it's a design problem. So that's something that you won't find a holy grail for. You just need to take it one design at a time. Now, the big challenge is also the flexibility of the material. So being able to design these structures and then deploy them and get into the right geometry and make sure that they are the right size, and all of these things, the simulation of all of these things that work together, that is quite tricky. It's a lot harder than saying, I'm going to take this piece of wood, I'm going to make a cut this way, and it's going to be there and it's going to stay in that shape. So getting to the geometry that you want is still a little bit challenging, and that has something to do with both computation, so being able to simulate these things. Then we get into material models, so you would need to have material models for that. But the material models for knitting are very difficult as well to simulate, a lot more difficult than other material models. So there's a lot less work that has been done by other researchers on this as well. So you can't really rely on that as well. It still needs to come up. And if it's done, it's not done on such a huge scale. So really simulating something for a small piece or for an entire structure is different. And even when we do have this, so being able to say, okay, this is the geometry that we want to build. You might have seen it with the node a little bit. Okay, this is the geometry that we want to build. But when you make a textile, you need to stretch it to that geometry. So which textile do I need to make? So you need to figure out which textile you need to make, which is a different geometry than your input geometry to get to the input geometry. So this kind of inverse problem is still something that is solved in a few ways, but is also a little bit tricky with the knits. What I find interesting is exactly this type of tailoring the material properties. And if you do that, you inevitably also have different material properties within the same patch. And once you start having that, the level of difficulty in terms of predicting these kind of things comes to the next stage. So there's that. And then even if we have all of that, so let's say we have all of these kind of things, I think constructing, so the actual physical work, that starts becoming, it's not a huge challenge, but it's also a challenge in the sense that we need to know in which order to do things, how to be able to do this. You can't just walk on a textile mold, but you can walk on a timber mold. So in terms of logistics on site, on how you apply things or how you apply the material to this, it becomes an interesting challenge to try to solve. And that also has something to do with not only the fact that you can't walk on a textile, but that maybe the geometries that you're trying to build are already a lot more complicated or difficult to get to than the usual box 90-degree geometries that we're used to. So now it sounds like a lot of problems, but of course there are a lot of people working on all of these kind of things. There's a lot of work being done on that. It's really becoming something that is adopted, and the next thing you might see it also with your work now and with the workshop is that you somehow need to take care of the entire chain. You need to be able to design it, you need to be able to simulate it, you need to be able to fabricate it, and then you need to know how to construct it. So right now what we're all doing a little bit is becoming all of the actors in the chain. But if we want industry to adopt it, well, there's not one single actor that does all of those. So you need engineers to know about it, you need architects to know about it, you need fabricators to have the knowledge for it, and you need constructors to have the knowledge for it. So you need a lot of different actors to start being able to play into it. So I think that's also one of the difficulties in this. But that's one of the difficulties that is not specific to flexible formwork or is not specific to knitting. It's kind of specific to new technologies in construction, right? So for them to be adopted you could take 3D printing, it's the same story. You would need from design to fabrication to have that knowledge in the entire chain. Does that answer your question?
It's a great answer. I get a lot of inspiration, and I also agree. From your answer, I came up with 3 more questions, but I don't know if it's okay to ask.
Sure,
here.
go ahead.
Okay, so so for the construction part, so what I'm confused, what I'm thinking currently is the automation process of it. Because we can knit it automatically, but because it is so intricate with intricate geometry, and it is also soft, so it's not like wood. We can pick robots to pick that up, but no robots can pick a fabric and stretch it to the right shape. So so I'm wondering, are we reducing the labor or adding more labors to the construction using the fabric formal, or do you think it can be solved anyway?
So I don't think we're adding more labor. Maybe it's just different kind of labor. If you've been to a construction site, what people need to do, even in what they're carrying around, and even needing to tie rebar a million times in a million different ways, or the type of labor in all of these kind of things, I don't think we're adding labor. I just think it's a different type of labor. So it needs learning. That's it. And if anything, it's a bit lighter than everything else. So at least in terms of health and safety, it might be a little bit easier on construction workers. I do think the automation of it can be figured out. We're working on some of these topics as well, but it's difficult. It's very long term, and and in the end, what a construction site needs is for things to be simple. And sometimes not having a robot trying to stretch it into the right shape is actually simple. If you have that, if you have the intelligence already into it, or you know to where it needs to go with simple measurements, you might be able to get there anyway. Or design in such a way, and that's also a question, right? Because we keep going towards precision and perfection, getting closer and closer to a particular thing that makes it more difficult to control if we get there. And I guess there's a moment where there's a trade-off, where you say, okay, we can stop with the precision here, and we design and accept certain tolerances, and then you can get it there in an easy way.
Yeah, it's a very nice answer. Thank you.
You're welcome.
So
Any more questions from the students, or should we wrap up? It is getting quite late in China. It's already 10 p.m. for them, and they've had a long day. We started class this morning at 8 a.m. for them. Tomorrow we'll start at 9, though, so they can sleep in a little bit more, right? But thank you so much. If there's no more questions.
Thank you for having me.
Wonderful. Great. It was really great seeing all the work, and I think I'm super inspired. Hopefully the students are also inspired seeing another kind of path to using knit as a way to build. So thank you.
You're very welcome. Thanks for having me.
Thank you. Have a good day.
You too.
Bye-bye.
And good luck with the rest of the workshop.
Yeah.
Yeah.
I'm curious
Please follow
to see.
and see our results. Hopefully we'll post some.
Please show me. I'm very curious.
Yeah.
I'm sure all the students will be happy to share it when they actually make something. So
And I think they will also like feedback from you. You can judge everything. Yeah.
Sure.
Just give some suggestions. Yeah.
Sure.
It's our
No
first
worries.
time attempting try to teach architecture students with knitting.
Yeah.
You know, from the zero.
And it's tough, huh?
Yeah, it's tough. We are trying our best. And thanks for Virginia, and thanks for Mariana. Have a good day.
You too.
bye-bye.